Page 4 of Euler's complex numbers chapter from HL. Use the complex numbers to find the distance of AB and the midpoint of AB for these two coordinates. The trick is that in this case they said to use complex numbers, so we translate the coordinates into complex numbers. So 3, 6 becomes 3 plus 6i. Negative 1, 2 becomes negative 1 plus 2i. Now we're going to find the distance AB by subtracting the x's and subtracting the y's. So we'll have 3 minus negative 1, which is going to be 4, plus 6 minus 2 is 4. So 4 plus 4i is the difference between b minus a. And if I want to find the modulus of this, I would square the 4 and square the 4 and take the square root, which would be the square root of 32. What about the midpoint between these two? So we would add together the real parts. We get 3 minus 1 is 2, and we would add together the imaginary part. 6 plus 2i is 8i, and both would be divided by 2. So we would get 1 plus 4i. So that would correspond to coordinates of 1, 4. So you can translate coordinates into complex numbers and then do complex numbers operations on them, and then you interpret the resulting complex number as coordinates. Number 2, OPQR is a parallelogram. OP represents Z, and OR represents W, where Z and W are complex numbers. So find, in terms of Z and W, OQ and PR. So OQ is basically Z and W added together, right? So Z plus W. So PR, which is that vector, is going to be W vector minus Z vector. So W minus Z. Okay. B. Explain from triangle OPQ why Z plus W is less than or equal to modulus of Z plus modulus of W. So the triangle we're looking at is OPQ. Okay, we're looking at this triangle here. So it says y is Z plus W, which is this, less than or equal to Z added to W. Okay, discuss the case of equality. Okay, so let's take a look at this triangle. So we have this triangle, and not the hypotenuse, because it's not a right triangle, but the long edge is Z plus W, and the short edges are Z and W. So remember, there's a property of triangles that any two sides of a triangle added together are longer than the third side. So since this is a triangle, that's why we can say that the third side is less than or equal to the two other sides added together, right? When would this be equal? This would be equal if the triangle was totally flat, right? So if it was totally flat and all the sides were parallel, then Z plus W would be exactly the length of W plus Z added together. Okay? Let's store this up over here. Let's take a look at part C. Explain from the triangle OPR why Z minus W modulus is greater than or equal to W modulus minus Z modulus. Discuss the case of equality. Okay, So remember, z minus w modulus is like this side here, right? It's like rp modulus. And let's rearrange this. So if we have z minus w minus or plus z, it's greater than or equal to w. Okay, so let's take, so our w side is that. So remember that if you have a triangle, that any two sides of the triangle are added together are longer than the third side. So in this case, the third side is w, and the other two sides are z and z minus w. So in this case, we're just saying that the two red sides of the triangle added together are longer than or equal to the blue side. And since it's a triangle, that's true. What does it mean when they're equal? So instead of having this triangle here, the blue side is going to be equal to the two red sides added together. So that would be like kind of like a really flat kite shape. So instead of being the way it is, it would be kind of like kind of like this. So the blue side would be here, and the red sides would be flattened up against it. Okay, so the red sides would be z and z minus w, and the blue side would be w. Okay, so in this case, we would have that z minus w plus z is equal to w. So basically in the book, what they do is they look at the triangle case. In the triangle case, they say proves that it's less than. Oops, that it's less than. And then they look at the equal case so that they can say in the end that the thing is less than or equal to. Okay? So first with the triangle, they say that it's greater than here. And then when they do the equality case, they say that they're equal, and then they put them together, and that makes the greater than or equal to. Okay? So that's why they do the equality case. Number 3, if z1 is defined to be op1 vector, and z2 is defined to be op2 vector, explain why z1 minus z2 is equal to p2 p1 vector. So let's start with the left side, z1 minus z2. And we'll substitute in op1, vector op1, minus vector op2. Now, minus op2 reverses their direction and adds them. So that's equal to plus p2o. Now we're going to reverse the order of addition. So we're going to have p2o plus op1. And you see how going from P to O and then from O to P1 is the same thing as going from P2 to P1. So that's why this is true. Number 5. Find the complex number z that satisfies this equation, given that the modulus of z is equal to 2 square root of 10. Okay, so let's see. Can we do this with algebra? Okay, so we do not want complex numbers in the denominator. How do we get them out? We multiply by the conjugate, right? So we're going to multiply 50 divided by z conjugate by z on top and z on the bottom. We'll get 50z divided by z conjugate times z. And that is subtract 10 divided by, and then we're going to do the same thing. We're going to multiply z by z conjugate and z conjugate also on top. That equals 2 plus 9i. Then we're going to see that the top, we can combine the like terms. Well, we don't have like terms, but we can combine the numerators. And that's equal to z conjugate equal to 2 plus 9I. Okay. What if we now multiply both sides by z conjugate? So we have 50z minus 10z conjugate equals to 2 plus 9I times z conjugate. I'm going to rewrite z conjugate as z modulus squared. Now, do you see how we're adding together the complex number and its conjugate? That could eliminate some imaginary parts, right? So what if we substituted a plus bi in for z, and we substituted a minus bi in for the conjugate? Then let's simplify that. So we'll have, or expand it, 50a plus 50bi minus 10a plus 10bi. So 50 minus 10a is 40a. 50bi plus 10bi is equal to 60bi. And that's equal to z conjugate squared equals, or z conjugate squared times 2 plus 9i. I think we can use the fact that z conjugate is 2 squared root of 10. Z conjugate squared is equal to 4 times 10, which is 40. So we're going to replace that with 40. Okay. Now we can divide, we can expand. So 40a on the left plus 60bi is equal to 80 plus 360i. And 40a is equal to 80, so a is equal to 2. 60bi is equal to 360i. So that's equal to, that b is equal to 6. So the answer is z is equal to 2 plus 6i.